It's been a while, and it's been a while means that I made a lot of progress with OpenEcho. I built new hardware, new software, new cases, tested more transducers, and so on. So buckle up, set your playback speed to 2, and let's go. OpenEcho is an open source project to play around with sonar hardware and to figure out what we can do on a DIY scale. For example, I wanted to get Arduino readable depth data from an Echosounder, and it's very hard to get Echosounders that have a data output that can be read by an Arduino. One of these is a standard Horizon DS41, but these are not produced anymore, so it's very hard to get depth data from Echosounders. So the first thing I did was to disassemble one of these lucky fish finder boards and read the data directly from the amplifier section of the board using one of my fast logic boards, which is basically an Arduino Uno. After I had some great success with that, I thought, why not build my own hardware? And then I found out about the TUSS 4470 IC from Texas Instruments, which is a small chip to drive ultrasonic transducers. This chip costs around €3 or something and takes pretty much all the engineering work from you, so you don't really have to care about all the electronics design and the amplifying and the driving of the ultrasonic chips. So you basically just put a frequency in, drive the transducer, and then listen for the echo to come back. And everything is amplified, filtered, so you basically get a raw echo output to your Arduino, which is very convenient because then you don't have to really engineer all the amplifier circuit, the driver circuit, the variable gain amplifier, and all the stuff that is very nasty to build. The TUSS 4470 is usually used in these car parking sensors and whatnot. And the cool thing is you can drive different frequency ranges. For example, 40 kilohertz for air, or 200 kilohertz for underwater, or up to 1000 kilohertz for very advanced underwater applications, whatever you like. The usual frequencies in air is 40 kilohertz, and in water it's 200 kilohertz. So all these marine grade Echosounders, this one, that is mounted in the hull of the boat, runs at 200 kilohertz. Some run at 80 kilohertz, some at 150, most of them are 200, and some are 455 or even higher. But usually 200 kilohertz is the range for depth finding on boats. To test this TUSS 4470, you can buy a development board from Texas Instruments, but it's around €300 or something. So this was kind of too expensive for me, so I designed my own board. That looks like this. This is basically just an Arduino shield that has this TUSS 4470 chips on board and connected to SPI and all the pins you need on the Arduino. Using this, I first started by driving a cheap 40 kHz transducer in air, and then switched to a 200 kHz transducer to test it in water. And this actually worked quite well. So one drive mode of the TUSS 4470 is to drive the transducer directly at the output of the TUSS 4470, which is very convenient because then you don't need a transformer to amplify the voltage to drive the transducer. But most transducers, especially in the underwater applications, need higher drive voltages like 200 volts or 300 volts or even more. These fish finders, like this one, runs at about 500 to 600 volts or something. So this is definitely amplified with a transformer inside. The downside of using a transformer is that you also need a matching circuit between the transformer and the capacitance of the piezo chip and the cable. You basically have to tune it using another capacitor. And this capacitor has to be quite voltage proof, so this makes it more complicated. And you need more measuring equipment to tune it accurately, which is bad. So the best case would be to drive this directly from the TUSS 4470, but you're limited to 28 volts because over that the chip will be damaged. On this board you have the option to choose between different voltage inputs. This could be the input from the Arduino, the VIN input, or also the XT30 connector. So you use this jumper to select what voltage source you want to use. Also on this board you can choose between different frequencies, like pre-selected, one is 40 kilohertz and one is 200 kilohertz. This basically sets the filtering capacitors for the TUSS 4470. If you need a different frequency, for example, you want to drive a fish finder or a side scan sonar with 455 kilohertz, you can select the custom capacitor position and solder your own capacitor in. Because I'm more interested in underwater applications, I built this. This is basically just a contraption to test this 200 kilohertz transducer that is glued in here with my testing shield. This is just a lid with a waterproof connector for the cable, and I have this TUSS shield with an Arduino inside this, and also a transformer on the bottom of this case. Let me try to... So there, the piezo is glued in here. Oops. The piezo is glued in here, and we have a transformer here and a feedback wire, that is the green one, that goes back to the amplifier part of the chip on this board, because now we have to get the signal from the piezo after the transformer. Basically how it works is the TUSS 4470 sends a pulse of, let's say, 12 cycles on the drive frequency, in this case 200 kilohertz, sends this to the transformer. The transformer amplifies this from, let's say, 25 volt to 250 volts, and then sends it to the transducer, then emits a sound signal on 200 kilohertz, and then waits for a signal to come back. The signal that comes back is also at 200 kilohertz and gets amplified via this, or goes back via this little line that is connected directly to the piezo, and then gets amplified by the TUSS 4470. And then filtered, amplified, and it gets filtered, amplified, and then sent to the analog A0 pin on the Arduino. And from there we can sample it and send it to the computer backend, which is basically all it does. Everything you can see here is open source, so you can copy it, download it, change it, whatever you like. These boards are made to be assembled and manufactured by JRC PCB mostly, so all the manufacturing data is with the LCSC part numbers, so you can order them directly there, which is very convenient, I think. And I think 5 boards are around 50 to 60 euros currently assembled and shipped to your house, so I think this is quite reasonable. Everything you can see is on GitHub, so there's a little bit documentation right now, but there is still some stuff missing. But I got some test results here, the videos I posted earlier, and some other information you might need. Also the links to the transducer, for example. This one is the one I used in the all-in-one transducer. This is a 18mm 200 kilohertz transducer, which is exactly this one, or this one. This is the same. And this is a very good starting point if you want to do underwater stuff. For air, you usually use a 40 kilohertz transducer that looks, for example, like this one. This one is a very cheap 40 kilohertz transducer. I also tested with that, but that works perfectly fine. But I also tested with very small transducers. This one is a 200 kilohertz transducer. But as the sensitivity of the amplification depends on the surface area, this doesn't really make sense to use this for large ranges. So for large ranges, the transducer area should be very large to get a meaningful echo back. I would recommend to use one of these piezo crystals to get a baseline or to get started, if you want to use underwater applications. If you want to be in air, I would recommend to use one of these. These are very cheap as well. The hardware will get shipped to you like this. So most of the stuff is already assembled. So you only need to solder the THT components, which are the XT30 connector, the THT pin headers, for the settings and for the connection to the Arduino, and the screw terminal for the transducer, but you can also solder the transducer directly there. Then everything else happens in software basically, so this connects to the SPI interface on the Arduino, and for GPIO pins of the Arduino for feedback and for driving the transducer. So the Arduino generates the driving signal or the driving frequency for the TUSS 4470, that amplifies this driving signal to the piezo crystal and then emits the sound on that frequency. The TUSS 4470 has to know when it starts, so it sends a pulse of let's say 10 cycles, on the drive frequency of the transducer, then starts the sampling process or the amplification process. And while the time goes by, it increases the amplification factor to get a better echo the longer the signal has traveled, if that makes sense, right? And then the amplified and filtered signal goes back to the analog A0 pin on the Arduino and then gets sampled from the Arduino and sent back to the Python backend. This is what the TUSS4470 test board looks like. We have this TUSS4470 right here, some components that are needed for this chip. Also, you can select the frequency, 200 kHz or 40 kHz, or if you have a custom frequency, for example, 455 kHz for side-scan sonar or whatever, you can select this jumper here and solder your own capacitor here. This capacitor value can be calculated using the formula on page 31 in the datasheet, or on the other design, I have some sample values you can use. And then you connect the transducer right here, and then you drive the PLC transducer directly from the TUSS44 from the input voltage you supply here, or on the VIN pin on the Arduino. And you can select the input voltage here by selecting the jumper on the left side or on the right side. So left side is XC30 and right side is VIN. On the VIN side, you can only go up to 12 volts because the Arduino gets fried after that. But on the XC30 connector, you can go up to 28, I think, for the TUSS4470 to work. Maybe even up to 30, maybe even 31 because the diode, but safe voltage is 28 volts. The higher the voltage is, the more energy you get into the transducer, which is favorable because then the echo is also stronger. For example, if you drive these 200 kHz transducer, in air with, let's say, 10 volts or something, you will get an echo, but the echo will be very weak and you only get a range of, let's say, 10 to 20 centimeters. If you drive it with 28 volts, you can get a range of about 80 centimeters to 1 meter. So the higher the voltage, the more energy you put into the transducer, generate more sound energy, and also get a better echo back. So usually it's better to have a higher voltage on these. Maybe? Yes. So yeah, you can also connect a transformer to the output of the TUSS4470. Either you drive it directly from the internal MOSFETs, or you can drive the MOSFETs with the TUSS4470. I haven't tested that, but driving the transformer directly from the TUSS4470 still works. But you only get, I think, up to 20 milliamps from the TUSS4470 on drive voltage, which is not a lot, but still it works for many applications and also in water with commercial transducers. So the layout would look like this. You have the TUSS output here going into the transformer. Then the transformer is, in my case, a 1-to-6 transformer. Then the voltage gets boosted to 6 times the input voltage. So for example, I have 20 volts input voltage 6 times, and then I get this to the transformer. The downside of using a transformer is that you have to match an LC circuit between the secondary coil or the inductance of the secondary coil with the capacitance of the rest here. So the rest here is basically the transducer, which has a capacitance that is around 200 to, let's say, 800 picofarads. The line or the cable you have, usually coax cable, so you have to consider that capacitance, and then you have to match this using these two matching capacitors to the inductance of this to form an LC circuit to the drive frequency of the transducer, so basically the mechanical resonant frequency of the transducer. You have to do this manually, sort of, so you have to try different values to get the best result. You can do that by measuring the output voltage or the peak voltage on the transducer. But when you add a measuring probe for the voltage, you will also increase the capacitance, which makes this kind of complicated to test. So I would recommend to connect this to your computer, plot the data in the software backend I wrote, and then see if the echo increases or decreases by adding capacitance, and see what the best results are. You can also simulate this in, for example, I did this in every circuit, but the results were not very good. Also, the inductance of the transformer is not really known at least for the ones I got. And also the capacitance of the rest here is not really known as well. After this board, I wanted to have a real device I can basically throw in the water and get data out directly to my computer. For that, I designed this. This is an all-in-one transducer circuit with an STM32F103, a CP2102 chip for the USB serial conversion, some other components for generating the drive voltage. For example, this one is a boost converter that goes up to 28 volts, which is configurable using a potentiometer. And then the TUSS 4470 with a transformer connected to it, where the piezo is also directly connected to the board. Yeah, this is what the design looks like. This is basically a disc that is 60 millimeters in diameter. Everything is on one side of this board, so in 3D it looks like this. So I have the STM32 here, the CP2102 USB serial converter, a reset button, input via USB. So you can directly solder your USB wire here. The boost converter that is here with the potentiometer here to set the drive voltage. And then the TUSS 4470 here, plus all the circuitry you need for that. And also a transformer here and the piezo on the other side. Also a DS18B20 temperature sensor to compensate for sound speed in water for different temperature ranges. So this is the first board I built for this all-in-one transducer. So I still have to figure out if it works. It's currently in manufacturing, or it's actually already in the post. So I will have to wait for a few days until I can test this out and write software for it. But I'm very much looking forward to this, because this would be very cool if this works with an all-in-one where I can just throw this in the water, have a USB output for the raw data. That would be very cool. And I also think that this might even get better results than the boards I built before, because I have some improvement with the ground, which is separated in a digital ground and analog ground. Also, the drive voltage is higher now. Before that, I used 3 9-volt batteries in series. That looked a little bit janky, like so. And these, this is pretty much the cleanest voltage source you can get. But the 5 volt from the USB converted to 28 volts should also work. I've seen this in a different on a different board, and that seemed to work fine. So I hope this works fine too. Yeah, for this I also designed a small case that is currently 3D printed on an SLS printer with nylon 11 powder. So basically a laser sintered nylon powder. I hope this is waterproof. We are still trying to get it tested to test the waterproofness using these discs. But so we have to figure out if that works. If this doesn't work, we will get this part on a lathe, which is not too complicated, I'd say. In this case, we have the board from KeyCut, which is this 60 millimeters, and overall it's, I think, 95 millimeters or something. In between, we have this groove where I put some Zika 522 sealant in it, and hope to seal it off with this lip on this side. And this is all screwed together with M4 screws, so in the end it will look pretty much like this. This will also be potted, either using epoxy or some silicone or Zika 522 again. Now, I'm not too sure about this right now. Probably I will just use Zika. Also we have this gland on top where I can get the USB cable through in a waterproof way, hopefully, and then see if it works. The parts are already 3D printed. I just picked them up from the Fab Lab. I got these printed, which is very cool because they can just throw it in their SLS printer together with some other parts, and it's basically for free. It was for free because they gave it for me for free because I think they like this project. This is a groove that I already filled with Zika 522, and this is the lip that goes into this groove, but only when this is hardened. And also this is glued in because I messed up the 3D printed wrap for this gland. So I had to glue this in, and from the other side with super glue. I hope the porosity of this material is not a problem that water seeps in, but it's not. It's only for testing. Beside these tests with this transducer and the transformer inside, I also tested with the commercial transducer, which is a a Raymarine CPT S200 kHz transducer that you can buy for about 150 euros or something. And these are usually built in directly into the hull of the boat. So you basically drill a large hole into the boat, stick this in, glue this in, screw this in with a large screw nut. You get this connector, which is a 9-pin connector, and you can figure out online what pin is what. 2 of these pins are the piezo crystal, and you can drive these actually directly without a transformer from the Arduino shield I built, which is very cool. And I got some good results I can share here. There is the short, and this one is the Raymarine CPTS 200 kHz transducer with about, I don't know, 5 or 6 meters of cable. And this Echo shield, directly driven transducer without the transformer in between. This is the reflection of the ground. This is about 6.50 meters, and there is even reflections inside the ground, which is like enough for this. And I have the transducer down there. I hope it's waterproof. When I connect that, usually only one LED lights up. The battery is basically flat, which I already knew because it was at 20 volts and not at 26 or something. So yeah, my fault. Damn it. Yes, and I think that might actually be it for now. So a lot has happened. Oh no, I forgot. Give me a second. Yeah, I forgot this. So I wrote this new software for it. Before that, it worked with Python and Matplotlib. Now I use Python and PyQt. PyQt is way faster than Matplotlib and usually used for front-end stuff and user interface stuff. So this is now the shield with the piezo connected here. Maybe I will screw it in like properly. So now the piezo is connected. Now I need a voltage source that is a little bit higher than. Nope. Wrong polarity probably. Yeah, that looks way better. Yeah, but the battery is empty probably. Yeah, so now I connected the transducer, the 200 kHz transducer directly to this board, so no transformer in between. And when I shoot this to the wall right here, you can see an echo right here. This is not very strong usually currently because I have this connected to only 12 volts because the batteries are flat right now. But if I move this to the wall, the echo comes back faster, and if I go back, the echo almost disappears and comes back later. Yeah, this interface is currently not finished, but I added that you can use different serial ports, connect these. This is more or less real time right now, and also an auto tuning for the gain. Also a depth detection from the board itself. So this is actually done inside the TUSS 4470, which is very cool because then I don't have to do the processing on the microcontroller, but can already do it on the TUSS 4470, which takes a lot of memory load or processing load from the microcontroller, which is cool. Also temperature when I have the other board. This is not implemented right now, but for the later board I already implemented this into the protocol. And yeah, everything open source on GitHub if you want to use this for free. And I think this is actually it right now. I'm currently still waiting on the PCB. I hope this will arrive this week. But the rest is already finished, so I'm very much looking forward to testing this all-in-one transducer in the water, and then I probably have to find a location where I can test this to the maximum depth, which is actually quite hard because in Kiel here we have like reachable from land is only 7 or 8 meters, maybe 11 at some points, but I have to test this at 25 meters or something later when everything else works. So I'm very excited to test this then. But until then, thanks for watching. I would really appreciate a like, a comment, or a subscription, a GitHub star, and whatever. So thank you very much for watching, and see you in the next one. Bye. Probably I should mention that the chip is called TUSS 4470. I'm not sure if I did that. Bye.